Okay, so good afternoon everybody again, and also everybody watching on YouTube. Uh, so in this afternoon we are going fishing now. So in the previous lecture you learned it's all about addressing the question, where is the fish? So I have my fishing rod, and we are going to address one of the techniques in inverse modeling, which is source reconstruction using beamformers. So there will be some repetition from the previous lecture, and this is quite healthy in the context of the toolkit. So just don't get surprised that you, or actually you should be excited that you see things again. So far in the course of the toolkit, we've basically addressed some temporal aspects of the data and also some spectral aspect this morning. So we are going to use those two dimensions, so time and frequency, and we would like to address a third dimension, which is space. So we want to uncover some spatial aspect of your data, pretending to not having time and frequency in it, but we are going to use time and frequency in order to retrieve space. So, or actually, the question for this afternoon is how you get from this monochrome image to this colorful image that is more funny to look at. So this person you already saw this morning, and there are 2 points I would like to stress again here. So there are 2 sources, a green and a red dot, and all of those sources project to all of the channels you might hook up to the scalp. And so one point I want to stress is that those 2 sources are characterized also by a time course, and the time course of those 2 sources is superpositioned on the scalp level. So all the channels see to some extent those 2 sources, and actually what we want to do is to reconstruct the time course, so not just localize the 2 dots, the 2 sources, but also reconstruct what is the time course, what is the source waveform. So the source waveform is that what we need in order to compute, say, connectivity metric. So superposition of source activity, you already learned, but let's repeat that again, has several consequences or several challenges for us doing inverse modeling, which are the following. So the visibility of the sources is varying across channels, and the time course of each source contributes to each channel. So this depends, of course, on the visibility, but you have a contribution of the time courses on all the channels you might hook to the scalp. An activity on each channel is superposition on all of the source activity. So not only a source projects to all the channels, but also on a channel there is information on all of the sources that are present. So in source modeling you have to deal with these 3 elements. So you have to find a way going from physiological source where the electrical current is present, through the body tissue where the electrical current is conducted, up to the sensor level where you measure your data. So finding a solution or a way through this, it's commonly known as forward model or forward solution, and finding the way back, finding a solution back, is called inverse modeling. So you learned a little bit out of that. So we are going to focus on a particular technique to find out where the fish is, which is the beamforming. So consider a source pictured here in red that is projecting on some set of channels you might have, pictured in blue. And what you're going to do in some of the inverse methods, for instance single and multiple dipole models, you will assume that there is a small number of sources that will explain most of the variance in your data. And the question you would ask is just where or how many are those small number of sources that going to explain my data. So you take a dipole, put it into the space that you want to reconstruct, and then fit it around until it matches your source, until it matches the red representation. So you basically compute a fit until you explain the data. So in distributed modeling you have the same situation, but in this case you just say, well, I assume activity everywhere, And by that assumption, I will also not only reconstruct my source that is here, but also all other activity at once. So the question you would ask is then, what is the distribution of activity over the entire brain? In spatial filtering, well, what the beamforming is one of these spatial filtering algorithms, you still take one dipole, but instead of fitting like in the single and multiple dipole models approaches, you assume that first the assumption is that a time course at a given location is uncorrelated to all other possible time courses or all other different sources. And you basically ask what is the likelihood at that location for a source being there. So you take a dipole and you start to scan your source space location after location until you're done with all the desired locations. So this is a scanning method. So there are different inverse models, but actually the data model we have is the same. So the data model we use is basically X. Now it's a new letter, and capital X, which is your data. And it's a linear sum of a source S1 times its lead field, plus source 2 times lead field, plus source n times lead field, plus some noise. So this is what the data is. And in a single and multiple dipole models, you basically want to minimize the error between model and the data in a least square sense. So you assume there are typically small number of sources that we are going to explain your data. And you basically what you want to achieve is that subtracting your model from the data, the remaining part should be the noise. Or you might decide to use a distributed source modeling, and then you say, well, I won't display all the activity. So you do that at once. You make a perfect fit of your data, so explain everything. But as Robert already stressed, so there's a problem with this overfitting, so you have to add some additional constraints that allows you to find a unique solution to the problem. So the data model is still the same, but instead of taking one, two, or several small number of sources, you just take many more, much more than the sensors. And what you want to do is you make a lead field matrix, so capital H is basically the lead field matrix of all these dipoles. You multiply that with your data minus the noise, and you want to have what you want is basically a capital S, which is all the sources in the brain in one shot. Okay, but then there's also the spatial filtering world, where you basically scan the brain location after location. So there are several methods you can use, but in this lecture we are going to focus on beamforming. And beamforming algorithms, also several of those are on the market. So we are going to focus now on the time domain beamformer, which is LCMV, the linearly constrained minimum variance one. But in the hands-on section we are going to address the frequency domain beamformer, which is the DICS method here. So what you basically do here, so the data model is still the same, but now we are focusing on one location at a time and pretending and put all the other location into the bracket. So we design a capital N, and this N constitutes a activity that we are not interested in. It's not only noise, it's all other activity as well, but we are going to focus on that location, and we assume that S1 is uncorrelated to the N, to all other possible locations. Next you focus on the second one. You assume again that the S2, the second source, is not related to all other N's, and you do so on and so forth until you finish with the locations you want to scan. Important to note here is the data model is the same and the assumption is different, which is you assume that the sources are uncorrelated. Okay, so how to? So if you want to do beamforming on your data, you should use field trip. And if you use field trip, this is basically how beamformer works. This is probably what you end up when you use field trip in your research line. So you would start with some defining of the epochs, then reject some artifacts, then do some pre-processing on your data, filtering, etc. But eventually would you would end somewhere here on those two functions, so FT source analysis and FT dipole fitting, and those two functions, there are several methods implemented there. So Robert already stressed that, but you basically either go for FT dipole fitting if you want to scan your volume space with a single or several dipoles, or you start with a 3D volume or cortical sheet, and for that you use FT source analysis, and there you can basically take the method of choice. So you can use distributed methods such as minimum norm estimates, but also beamforming techniques such as the LCMV, a time domain one, or DICS, a frequency domain one. Okay, so how are you going to do that? So of course you have to design the experiment first, and this point appears somewhat trivial. Well, of course I have to have an experiment, but in the context of beamforming, this is really important. So beamforming actually starts here in designing your experiment, because it is one of the techniques that it's going solely rely on your data and the experiments, how you design it. It relies on a contrast, so you have to take care of your experiment. How is that designed? So next we'll measure brain activity, then do some data analysis, pre-process the data, and do some time frequency. So in the case you want to reconstruct oscillatory activity, you would do time frequency analysis, define your time frequency tile of interest, and then eventually you source reconstruct it. So stage one is the design of experiment. So in beamforming, you really, what is recommendable is to have a clear baseline, a clear segment in your data where your participants are attending but not doing the task yet. So consider that situation. This is a phase-place association task. So what you really want to know is what happens in the brain while a participant is retrieving a previously learned place associated with that phase here. So you want to contrast this against a condition where the participant is just attending to the experiment but not retrieving the position yet. So therefore you design your the timeline such that you have a baseline where you have this condition of attending to the experiment but not doing the task yet, and also you avoid, for instance here, you avoid the presence of artifacts, because this is gonna obviously make some more problems. And also artifact is the motor responses that you might ask from your participants in order to check whether they are doing the task or just daydreaming or doing something else. So you demand a response, but you're not interested, or often you're not really interested in the response. You just check whether they are doing the task. And therefore you delay that. So you want to have a sufficient length of stationary signal that you're going to use in beamforming. So it relies on a covariance matrix, and that covariance matrix is built from your data. So we're gonna get into it a little bit more in detail. But it's really important that if you plan to do beamforming in your research line, just start with the design of experiment. Okay, so then you are going to measure brain activity, obviously, with imaging and EEG, but it's very also recommendable to record activity that you don't want to reconstruct, such as the movement of the eyes, blinks, cardiac artifacts, etc. This is also an important point. You have to know the relationship between the brain and the position of the sensors or electrodes, so ideally we'll record that. Of course, you want to reduce head movement, so ideally the head or the source in the brain you are interested in is not moving around. And also, in most of the cases, you should, if it's feasible, you should collect an MRE scan of your subject, such that you can make some realistic estimate of the volume conductor. This fifth point is, are you clear what that means? Okay, okay, you're not clear? So a localizer task is, suppose you're interested in how a emotional stimulus or affective node of a stimulus is amplifying the processing or amplifying the activity in early visual cortex. Okay, this is what you're interested in, and you can say, okay, I'll take a neutral stimulus. I'm gonna perform a classical conditioning experiment. I'm gonna make it really aversive, and then I'm going to test what is the affective node of that stimulus, what is the influence on the early brain activity in the visual system, for instance. So if you want to do this, instead of scanning the whole brain and searching for a particular location that is doing this, you first would identify the location that this non-conditioned stimulus is processed in. So you perform a localizer task before you start the conditioning, and you determine the exact location. So you're not going to have multiple voxels and locations that you need to correct for then, but instead you're going to have one or two, or the location where the stimulus is actually processed. Then you're going to add the affective node to it, and then you ask, so is there a effect of emotion? Of course, this is not possible and not applicable every time. So therefore, just in case it's doable and feasible, just do it. Stage 3 is data analysis. So you learned already how to segment your data. We addressed some artifact removal topics, but then after you're done with this pre-processing, you are going probably to do a time frequency analysis, just like you did this morning. So what is plotted here is time. So at 0, the phase is coming, and what you see is basically some increase of slow frequency power here, and probably reflective for the evoked activity at the beginning, and then some decrease in power around 10 Hertz. So you might ask, oh, okay, I want to know where is that activity represented in the brain. So in other words, beam this time frequency tile. So from say 1.1 to 0.1, I'm sorry, to 1.1 seconds. So it's a 1 second, and I want to know the 10 Hertz activity. So we are taking temporal aspect of the data, spectral, we are going to reduce that and ask where is that in the brain. So, because your frequency resolution is 1 Hertz, you are essentially going to get a bandwidth of 9.5 to 10.5, and you reconstruct that, and you address the question where this time frequency phenomena is happening in the brain. So it's quite easy, right? So you might also go and say, well, I'm not interested in that particular stimulus component. I'm actually interested in where the difference between conditions is happening. So, and you perform your statistical analysis on sensor level, say, and you can reject the null hypothesis. So there is a effect. So you might want to just represent the special distribution of that effect. So where is the brain in the brain is that happening? So if you consider our place-phase association task again, actually there were two conditions. So the participants retrieved the association just after learning, which is that condition, labile, and they retrieve it just 24 hours after they slept overnight. So the association between the place and the phase is stabilized. This is what stabilized means here. So you make a statistical contrast of these, and you find out that there is a group differences or condition difference, which is in this time frequency tile, and you say I want to reconstruct this in the brain space. So you're interested now in a window of 200 milliseconds, 0.7 to 0.9, and a frequency space of 70 to 90 Hertz. That's all good, but you learned this morning that is not going to work, because your window is 200 milliseconds or 0.2 seconds, which gives you a frequency resolution of 5 Hertz. So if you center your time frequency window of interest around 80, so this gives you a time frequency tile of 77.5 until up to 82.5. So what are you going to do? You learned that this morning. I bet all of you know. Just say it. So, you want longer time period, very good. But I'm interested in the shorter time period. I want to know only the 200 milliseconds. Exactly. So you are going to make a smoothing of the frequencies. So how you do that? By using, yes. All right. So you're going to increase your smoothing, frequency smoothing, without changing the length of the time window. So you could, but we don't want that now. So we're going to use multi-tapers. So just a reminder again, more tapers for a given time window will result in more spectral smoothing. This is what you want. So you want more spectral smoothing. And now several orthogonal tapers are used for this particular time window of 200 milliseconds. And subsequently power, but also the phase estimates that are needed for the frequency domain beamformer to work, are calculated for each of the tapered data segments, and then all of these are combined. So this is how you solve the problem of the window being too narrow and the frequency you're interested is too, the bandwidth is too large. So now you want this, and if you use 5 tapers, you get pretty much what you wanted. You get a time frequency tile that is 200 milliseconds wide and from 65 to 95 hertz. And then you create a map. Yes?
Would it be also possible to just use less frequencies, so maybe from 77 to 82?
Of course.
Same areas afterwards?
Of course, this is possible. But the question you want to address is, where is my statistical contrast that I found on sensor level represented? And your statistical contrast you found on sensor level by correcting for multiple comparison, etc., is from 65 to 95 hertz and from 200 milliseconds around the 0.8. I don't recall exactly. So yeah, that is possible. It depends. It just depends on what question you want to address. In that case, it's just where is the statistical contrast represented in the brain. Okay, so some field trip syntax. So if you want to do that, this syntax is probably familiar now to you. What is different now is that in the CFG output, there's a new configuration option here. You also output the cross-spectral density metric. So the output reads power, POW, and CSD. And this contains also the phase information that is required for the DACS beamformer to work. And the rest you basically specify your time of interest, frequency of interest, the window that you are going to use, and the smoothing frequency. And then you get a structure called FRAC that you need as an input to the function FT source analysis. I'm having difficulties with my mic. Okay. Good. So what is the question in beamforming? So what is the, basically, we have this red arrow here. So what is the activity at the source S, at a location R, given the data we have X? So I just said that. So we are going to explain now the concepts behind the beamforming on a time domain level. But if you understand that, it's just easy to translate that to the frequency domain beamforming techniques that we are going to do in the hands-on session. So this is what beamformer is. You estimate the sources with a W. And W is a set of coefficients, also called spatial filter, that allows you to go to estimate. So S hat is the estimation of your source, to estimate the sources that you are by considering the data that you measure on the sensor level. So the concept is, again, you have some observations on your sensors of a brain signal or signal stemming from the brain. You discretize the volume into a regular grid or several locations, and you start to scan them location by location. So you ask, what is the time course of activity? Man, I'm sorry. What is the time course of activity at that particular location? You write it out. Then you go with the next one, and so on and so forth until you scan all the locations you want to scan. And then you basically produce a nice picture. But here is an important point again. So because you designed your experiment to have a good baseline, now you can go and say, well, I want to contrast the activity against the baseline here with my actually task condition. So I'm interested actually in the activity during that interval. And you basically make a SPM map, which in that case gives you a nice focal reconstruction of induced gamma band activity, because you took care of in the design of experiment. You started with stage 1, the design of experiment. That allows you to be precise in your source reconstruction, at least in beamforming. In addition to that, you can say, well, I have now all my time courses. So you're not only localizing, but you're reconstructing the time courses. So I want also, what I want is actually having a seed region, say here. I want to know the correlation in time between this seed region and all other time courses I estimate. So this is also known as connectivity analysis. So you want to know the communication between the different locations you scan. And then you can also produce this SPM map with the contrast or your connectivity map of interest. So all of this is also known as creating the blobs. All right. So the next question is then, what is a W? How I'm going to compute this? So I need some weights in order to go from my measured data down to the sources. So we are going to compute that using a forward model first, where you basically ask the question, how is a source visible on the sensor? So you make a prediction. What is the data given a source and a particular location? Having a good forward model ensures that you have some specificity. So you're going to have a beam spotlight to a particular location based on your forward model. But then you also need your experimental data. It is a data that you have that's going to that allows you to compute the beamforming solution. So most often you're going to use some contrast, and this is in most of the cases say activity versus some baseline, and this gives you specificity of your effect. So you don't want to be only focal zooming in a particular location, but you also want to make a specific claim about this location. So let's look a little bit in detail into the forward model. So basically these are the questions you want to address. So how is a source at a given location would be seen by the sensors. So here is our S. Now the red arrow, it projects in a different strength to the sensors, but it projects to all of them. So this is still important. There is a linear superposition. And basically now we are going to take some pictorial representation of this forward models and the sources, which is in that case, S is going to be now a box, a horizontal box, which is basically a source time series. Then we have something unknown here. And we have also our data, which is, say, channels by time points. So it's a X matrix. And what we want, obviously, it's the forward model. And it is this H that constitutes the lead field, or gives us the forward model. And this is the data model we are using. So for now, we are going to focus on this graphical representation of the actual beamforming gradients rather than computing the mathematics behind it. So you have to just keep in mind how is our data model organized in this pictorial view. So in computing the forward model, the first thing you would like to know, or you actually need to know, is where is the brain with respect to the sensors. And we have several filter functions that will allow you to answer these questions. So the first one is ftplot sensors, or ftplot sense, which is going to read the structure, that graph that is in your data, and is going to plot the sensors, which are plotted here in green. So this is the sensor array. Then you could use ftplot vol to plot the actual volume that you that represents your head model. But if you are not that far yet, you could also, and you have some access to head shape points, which are typically obtained on a regular basis in 4D and Electro machines, but not so often in CTF. But in any case, you could read that file and plot the actual head shape, which are the red points here. So those three functions will allow you to look at the representation or the correspondence of sensors and head position. And then in that particular picture, you might have spotted already that almost half of the brain is outside the helmet. So this is not a situation where it is done for training purposes or something. This is a real data that might happen to all of you, and is not depending on experience. It happens often when you measure in supine position. But what I want to stress here is that you have the functions in Filtrip to check whether not only where is the brain with respect to the sensors, but does this really make sense? Should I use that if I know the answer? Because you could check, say, this is a visual experiment. You could say, well, I'm just checking on occipital sensors where I see a evoked activity, right? So I have a visual experiment. If I see a evoked activity on occipital sensors, that's good enough. But this is not good enough. Because you would see some activity. This to me looks like a good visual evoked response. Maybe it's a little bit weaker compared to all my other subjects, but I'm not going to throw out a subject because the response is weak. Well, in that case I will, because this is going to reduce my statistical sensitivity in the end. So it's going to increase the variance, and then I'm not being able to reject the null hypothesis. Because something happened during the measuring the brain activity. Stage 2 is equally important as the tricks later on. Okay, bottom line, check the position of the head with respect to the sensors. Okay, but in most of the cases you will do a great job. So this potato is now perfectly positioned into the sensor array. Then you're going to start, you ask, you are working with the function FT source analysis, and you want to do a DICS beamformer. And what you need to do now is, you know the position of the brain with respect to the sensors. Now you have to, it is covered namely in the structure FREC and a substructure GRAD, which has all the information about the sensor position, coil orientation, etc. What you want to do now, you want also to, you have to say how many and which are the locations you want to scan actually. So this is also known as a source model. You can create that yourself, or you also let Filtrip create it. You just get the regular grid. You just need to specify the dimensions of that grid. And then you discretize basically the volume. So you're going to scan on each of these locations. It's up to you how coarse or how detailed this grid is. It's just your decision that you have to make. And this you do with the function ft prepare source model. So next, you have to compute the potato, basically, the volume conductor, which can be, so you specify cfg.vol being a head model. Now, head model, you have to create it yourself. And there also, Robert explained that to you just a couple of hours ago, that it's your decision what is the head model, how is that the geometry should look like. So you could go for a sphere or compute some realistic ones. It's just up to you. But you need that in order, so you do that with ft prepare head model, and you need all these three components in order to be able to compute the h the gain matrix, the lead field matrix, or just our column vector H here. So this is also called the lead field matrix. Okay, so we said there are two things needed, the forward model and the experimental data. So now we know how to compute the forward model. So this means we know how to get from source to data. This is the forward direction. What we want to address now is how do we get from data back to the source. How we are going to estimate S hat. And we said that we are going to use a W, which is a spatial filter. But what is that? What is a spatial filter, or what do we want a spatial filter to do? So now consider that graph. In the horizontal plane, there are 4 sources, and let's say 2 of them are active. We're interested in the one in the second place, and there is also an interferer. So if we take a single dipole, or we are going to reproduce this, we surely will be able to reproduce the maximum activity of that particular source, which is basically, in this case, called a general filter. So we are reconstructing this, but nothing more, nothing less. So actually what we want to do is we want to have an ideal situation, an ideal filter that allows us to have this type of response. So we we allow sources to be characterized only at the location of interest and not on all other possible locations. And instead of having an ideal world, we have an optimized world, or optimized filter, which is now this line here, that basically says we are estimating as good as possible the source of interest, but at the same time we're trying to suppress all other interfering sources. So this filter tries to suppress the interferer and to output as much power as possible at the source location of interest. So this is also called the unity passband. So put as much as possible in the interested the location of interest. And the main concept behind this is the following. So we have space again with our source, and we are going to compute a filter with unit passband, which looks like this. So there is a maximum output in the source location of interest and no output else. So for the next one, we compute this. However, in our optimized case, it actually looks like this. So we still have a maximum output and the location of interest, but there's also some spatial leakage elsewhere. So there are other sources that are not optimally suppressed. For our earlier source, the filter output is probably like this, something like this. So you still get a maximum output here, but there's also some variability elsewhere. So in ideal world, you might have this true source activity, and you have your perfect filter. You're going to reconstruct this activity. But since we have this type of output, this type of filters, your estimated source activity might look something like this, which is still okay. So instead of suppressing everything, you will try to minimize the filter output as good as possible. So we want to produce a filter output that is tight as good as possible, that is focusing on our location of the interest and suppresses all other interfering sources as good as possible. So minimize the total output of the filter. Again, the question is how we go from data to source by using the W, and now we want to compute this W. So how is that really computed? So H times S is what? What should I write on that side? X. Okay. This is right. So this is our data model. So now we want to do this. So we have the X, and we want to estimate the source, and what we want also is the W. So if you look at those pictorial representation. You could take this part of that equation and put it here. So this is still valid. W transpose times H times S is the estimation of our source. So now let's focus on that equation. So instead of focusing on your given source and estimated source, focus on the transpose filters times a lead field. So say we have a purple source here, and this is the way we are going to estimate that given the data. And a unit gate means you're going to divide each side of that equation by the source strength, and this is going to result in W transpose times H is equal to 1. So there is a maximum output at that location. And you want to do just the same for the blue source here. You might have some other sources, but what you don't want to do is you don't want that the output of the purple source, the weight of the purple source times the lead field of the blue one should result in 0. This is what you want. And you want this for all possible combinations. So you want to zoom in into the purple source by blocking, at the same time blocking out, so the rest should be 0, and at the same time you block out all other interfering sources. So you make a beam, you zoom in. W transpose times H of a source I equals 1 is called a unit gain constraint, so you want to have a maximum output. And W transpose I times HK, so W transpose purple times H, say blue, should be 0, which is in generally cannot be fulfilled. So what we want to do is to minimize the variance of the filter output. So we want to minimize this. We cannot force it to be 0. But now you're looking at that slide, and I bet you're thinking about how I'm going to minimize the variance. This is how. So again, our situation is W transpose times data is equal, our source. So the variance of that source time series is basically the time series times the time series transpose. So this is the power of, or the variance of S. So now S is equal this. So you take this and put it there. And since S is equal this, you can take it here, just transpose it, and put it here. So now you're going to focus on this middle part. So X times X transpose. And this middle part is your data. This middle part depends on your data. And this middle part is also called a covariance of your data. This is the magic in beamforming. So it is the covariance of your experimental data that allows you to minimize the filter output, to minimize W. This is the formula Robert just introduced to you in the previous lecture. The formula is not so important. What is important is that in that formula is the forward model present, H, and also your experimental data. So we started how you do it with the forward model experimental data. So here is the case where your experimental data is present, the covariance is built on your experimental data, and the forward model, the H. Okay, so the ingredients are again forward model, which consists of the potato, the volume conduction model, the sensor positions, and the points you want to scan. So if you compute that forward model, you could also plot it. So this is how for this case 3 sources, how these 3 sources are visible on your sensors. And then you have your experimental data. So in the time domain form, you compute the covariance. We just learned about that, which looks like sensors by sensors. And you basically compute the correlation between those. So there is a high correlation of a sensor with itself, but there is also some with far distant ones. And the positions, the sensor positions are hidden in a frec.grad. The cross spectra or the covariance matrix in that case is a cross spectrum is also in Freck dot cross spectrum. So there is a matrix that you need to compute the covariance matrix, and then you make a call to FT source analysis by specifying the method of choice, which is DICS, your source model, your head model, and as an input you have to use Freck that consists or has the grad structure and the cross spectra in it. Okay, so why you should do that? So what are the strengths of beamforming? Well, obviously one of the major advantage is that it's easier to make an average across subjects or compute SPM type statistics, and it's not so easy if you have some single or multiple dipole scanning methods, because it's hard to decide which of those dipoles I should combine or are reflective for those two here, for instance. It's a obvious reason. And yes, so it's suitable for SPM-like statistics, also because you the activity that you estimate at a given location, you do so independent from all other locations. You don't make any assumptions about the number of the sources, amount or location of the sources. You just scan location by location and ask for the likelihood of activity being in that location. That's all what you do. And also quite often, so it's not always the case but quite often the beamforming gives more spatially focal representation of brain activity. It's not that in contrast to minimum norm estimate, for instance, where you smooth the image, it just quite often is rather focal representation. Well, that's all good, but you made some assumption. And the assumption you made is you assume that the sources that are present in the brain are uncorrelated. So this is an illustration of the seminal paper of Barry Van Veen in 1997, where this particular time domain beamformer has been introduced. So what you see in that illustration is just 2D plane, and in the z-axis is just the magnitude of sources. So on the right side, there are two sources that are, say, what, some 15 centimeters in the y direction apart, and some activity. So you basically see two peaks, but also you see two peaks here where the sources are, say, 2 or 3 centimeters apart. So the main message here is you see two peaks with a particular magnitude. This is the case where those activities totally uncorrelated. Now you might add some correlation to it, so you make them mildly correlated. So what you should realize now is that you are still able to reconstruct two peaks. What you are lacking is the real magnitude. So one becomes, for instance, smaller here on the, say, right side. And in the case of sources being close to each other, they start to merge together due to the correlation. And now you go in the extreme example and say, well, I make them perfectly correlated, and now you're basically seeing just one peak. In this particular case, it's just basically nothing. So you're not able to reconstruct the true location of the sources. So this is a limitation of the beamforming, that in this limitation you should consider when you perform beamforming analysis to your data. However, this limitation does not mean that you cannot use beamforming to, say, evoked activity. So probably the strongest case where we can say, well, this is on purpose and correlated, I expect correlated sources, is, say, an auditory experiment where you send two tones simultaneously in both ears. Okay, so in that case you would expect, at least in part, quite a lot of correlated activity in both auditory cortices, right? So let's consider that case. So if you do so, you might end up with an event-related field that peaks around 100 milliseconds, which is known as a M100, or in the EEG case is N100, over, say, left sensor size, what is plotted here. And then the syntax you would use in field trip is you have to compute this event-related field, right? So you segment the data, use the FT time lock analysis in order to compute the mean. This is what you did yesterday, and you end up with that time course. And so let's call this time lock, the red TLK here. So in order to compute the LCMV representation of this, so you call the FT time lock analysis again with your event-related field as an input. But in addition to that, you specify that you want the covariance estimate to be present in the output, and also what is the window of the estimation of the covariance matrix. So in that case, some 400 milliseconds around the stimulus zone center. So in that output AVG, there is the covariance matrix present. So this is what is needed in FT source analysis in order to compute the LCMV representation of it. So you basically specify CFG method LCMV, and you output an image, which will look like this in that case. So we have an auditory experiment. We expect sources in the auditory cortex. And what we see there, here, at least for the right side, we are satisfied with, right? So this is a thresholded map at, I think, 50% of maximum. So we have some confidence to say, well, what I see here in the right auditory cortex is reconstruction of the auditory activity, given that I have an auditory experiment and I stimulated simultaneously. So for the left side, the reconstruction is a little bit off. There's also some other activity going on here, so we don't have much confidence to interpret this. So we would say, well, I'm happy with my right auditory cortex reconstruction, right? But there's also an additional way to go, which is not the way to go, but is an alternative. And this is, instead of taking the event-related field as an input to during the estimate of the covariance matrix, you take the actual data, so the single trials you have, and you estimate. You just do all the same, but the covariance matrix is now estimated on the single trials, and then you call source analysis again, and the picture you're going to get is now looking like this. So now you're able to reconstruct, well, I would say with quite confidently, two blobs located in the left and right primary auditory areas. So their spatial extent is not so important right now. So we don't know whether they extend that much like they do here, because it's just a threshold at 50% of maximum. But what I want to stress is that it depends. So the limitations of the beamforming, they are actually limitations of you making choices and assumptions about the data. So if you're interested in the common activity of, say, 100 trials, the mean, reducing some alpha components and whatever, you have to compute the time lock structure. You have to compute the mean across all trials. And then you go for that source localization of that activity. So you might end up here. But you could also do the other way. So you estimate your covariance. You take your data again on a single trial level, and you are able to reconstruct the location, in that case, where this initial activity is happening. So far, we stress that it's your data that is important. So the covariance matrix, or the CSD matrix, the cross-spectral density, is based on your data. And this also means that you have, if you have differences, if you have several conditions or several data sets, and you have signal-to-noise differences in those data sets or whatsoever, so if you have a different estimate of your covariance, this would also mean that you are minimizing the variance differently, so your filter output is different, so the spatial leakage is going to be different, which finally means that it might be that you have three situations, a red, blue, and green condition, where you want to know the difference between those three. You compute that, you map that on the brain, and you find differences, but it could be that those differences are driven by the filter output, the filter output being different and not by the difference in the brain activity per se. You all understand this? Okay. So a solution to that is instead of computing the W for each condition separately, you have your two conditions, you segment the data like you do, but before you compute the W, you pretend those data to be one. So you append the data again. You compute your W, what is then called common filter, and then you separate your data again. So you multiply W transpose times your data, which is the green one, and the same W, the same filters with the red one, and then you are plotted on the brain surface or in the 3D volume. And now if you find differences now, it could be other reasons why they are there, but at least you can say it's not due to my filter being different, to my W being different, because I computed W to be the same in both conditions. So this is likely that the differences you might find here say real. This is called the common filter approach in beamforming. So we are going to address that just in several minutes from now. So the syntax there is you keep everything just the same in the like in the normal situation. You just add CFG keep filter yes, and this means that in your output structure source there will be a field called source.afc.filter, which is going to be the W or the filter coefficients that you compute here based on the both data sets together. All right, so to summarize, we went to a fishing technique called beamforming, and I believe you know now that this is not really a source reconstruction method, but it's actually a scanning method, or it's a really source reconstruction method, but it's more of a scanning, so you go from one location to another. And you make two constraints, so you want to have a maximum output at a location of interest, but at the same time, given your data, you want to adaptively suppress all the other interfering sources that that you are basically not interested in. So beamforming makes use of a covariance of the data and the actual forward model. How is a source seen by the sensor array? Beamforming is possible in time and frequency domain. So we explained the beamformer now in the time domain, but now you're going to learn how to apply that in the frequency domain. It's just important that you grasp the main idea, that you have to compute a linear set of weights, and it's your data that allows you to adaptively suppress interfering sources. In beamforming, you don't make an a priori assumptions about source configurations and locations, you just scan them. But what you assume is that the data is not correlated. So the sources are not correlated. The source time series are not correlated to each other, which is known as a limitation, but it could also be a strength. So in that case, beamforming is applicable in many cases. So there are most of the cases probably in the brain the sources are not really correlated, but you just have to keep in mind that if you have a high correlation, you are not going to reconstruct the activity with much confidence. And with that, I thank you for your attention. And yeah, if you have questions, go ahead.